In this video, we're going to continue with our exploration of angular momentum, and in particular, we're going to talk about ladder operators or raising and lowering operators in angular momentum. These are going to be very similar to the ones that we saw for the algebraic solution to the harmonic oscillator. We'll first talk about angular momentum and review what we had in the last video. Then we will talk about eigenvalues, eigenfunctions, and the ladder operators. So, the quantum mechanical operators for the components of the angular momentum in Cartesian coordinates, as we derived them in the last video, are Lx is minus IH bar Ly d by partial with respect to z, plus IH bar z partial with respect to y, and similarly for Ly and Lz. The operator for the total angular momentum is therefore given by L squared is equal to Lx squared plus Ly squared plus Lz squared. And you'll note that we're always going to talk about the total angular momentum as L squared, because that way it's a magnitude. It's L vector dot L vector. The commutation relation between these operators, as we derived last time, are that Lx and Ly don't commute, but they give you IH bar Lz. Similarly, Ly, Lz give you IH bar Lx when their commutator is calculated, and the commutator of Lz, Lx is equal to IH bar Ly. And once again, we move these subscripts along in a permuting arrangement so that we move them to the left and wrap the one on the left off over back on the right. So here we have Lx, Y, Z, here we have Y, Z, X, and here we have Z, X, Y. We also have the commutators with L squared, and in this case, all of the three operators of the three different components of L will commute with L squared. L squared commutes with Lx and Ly and Lz. Now, what this means is that L squared commutes with the vector L, because it commutes with each of the components. But more importantly than that, if we go back to look at what we had discussed about the formalism in quantum mechanics, is that when you have two operators that commute, they can have simultaneous eigenfunctions. So we're going to invoke that and say that we can find simultaneous eigenfunctions of both L squared and Lz. And we choose Lz because it's a special direction in spherical coordinates and cylindrical coordinates, and that's eventually where we're going. So Lz is the one we choose. We didn't have to choose. We could have chosen Lx or Ly, but we're choosing Lz by convention. So we'll say that we have eigenvalue equations for each of these operators, and they have the same eigenfunction f. L squared applies to f, gives us lambda times f, so the eigenvalue is lambda. And Lz applied to f gives you mu times f, so the eigenvalue here is mu. And we're going to assume that because these two commute, these both are eigenfunctions of these two operators. The same function is the eigenfunction of both. And we'll see where that leads us. Now we can solve for f and determine what these functions are and how we generate them by using the so-called ladder operators. In this case, for angular momentum, they are raising and lowering operators, and what they raise and lower will become obvious in a little bit. So we have L plus minus is equal to Lx plus or minus ILy. So very similar to what we had before for the raising and lowering operators in the harmonic oscillator, except we have no constants here. It's just Lx and Ly. So let's take a look at what the commutator of Lz and L plus minus is. We're going to take the commutator of Lz and L plus minus. And we know the rules for commuting Lz and the components Lx and Ly. And L plus minus is simply Lx plus or minus ILy. So this gives us the commutator of Lz and Lx plus or minus I times the commutator of Lz and Ly. Well, this is really very easy to do because we know the relationships. So the commutator of LZ and LX is IH bar LY because it's in the proper permuting order. The commutator of LZ LY is minus IH bar LX, and there's an I in front. So we have I and minus I, that gives you 1. And so this just gives you H bar times plus or minus LX, the minus sign cancels, the i's go away, plus ILY. Or if we pull the plus minus out, then we get plus or minus H bar times LX plus or minus ILY. But now we've recovered L plus minus. So we get plus or minus H bar times L plus minus is the result of the commutator of LZ and L plus minus. We can also calculate the commutator of L squared with L plus minus, but that's easy because L squared commutes with each of the two components that make up L plus minus, so it must commute with L plus minus. Now, let's imagine that just like in the harmonic oscillator, we make a function which is L plus minus applied to F, where F is the eigenfunction of L squared and of L sub z. So we're going to make a new function L plus minus F. Let's see what that gives us. Let's see what happens when we then apply L squared to that new function. Well, we have L squared applied to L plus minus F. Clearly, because these two commute, we can swap them without penalty. And so we can apply L squared directly to F, and we get L plus minus applied to L squared F, applied to F. And that's just L plus minus times lambda F, or lambda times L plus minus F. So what this is a new eigenvalue equation with the same eigenvalue. So by applying the raising or lowering operator of angular momentum, we get that we have the same eigenvalue for the new function. And it is still an eigenfunction of L squared. So much as with the harmonic oscillator, what we're doing is we're converting this to a new function. And we can build up a series of functions by applying L plus or L minus continuously. What about applying LZ to this new function? Now remember, it was an eigenfunction of LX, of L squared. Is it now also an eigenfunction of LZ? Well, we have L plus minus applied to F, and we apply L sub Z to that. But these two don't commute, so we can't do the same trick as before. However, what we can do is we can add and subtract L plus minus LZ applied to F. So flip these around, add and subtract those two terms. So we have now three terms applied to F. The first one is the one that we had before, L sub Z, L plus minus. There it is. Then we have minus L plus minus L sub Z. And all that can be applied to F. Each of these is applied to F. But now we've made this suggestively like a commutator. Then we have plus L plus minus LZ applied to F. And now this is easy because we can apply L sub Z to F and we get an eigenvalue, that is mu times F again. So when we expand that, we get for this the commutator of L sub Z and LX, L plus minus applied to F. And here we get L plus minus applied to mu F. Well, mu is just a constant it can pull through, but you remember that LZ, L plus minus is just plus or minus H bar times L plus minus, and then this is now applied to F. And here we have L plus minus applied to mu F. And so we can write, when we pull the mu out, we can write that L sub Z applied to the new function L plus minus F gives you an eigenvalue. It gives you the function back again and an eigenvalue, which is mu, which was the eigenvalue of the original function F, plus or minus H bar. So you can see now what it's raising and lowering. The L plus minus raises and lowers the eigenvalue of the L sub z operator, but the function that comes out of applying L plus or minus to F is still an eigenfunction of Lz. And it's, of course, an eigenfunction of L squared as well. So this new function also sits in the set of eigenfunctions that are eigenfunctions of both L squared and Lz. So L plus creates a new eigenfunction of L sub z, whose eigenvalue has been increased by h bar, and L minus creates a new eigenfunction with eigenvalue reduced by h bar. Well, there must be some upper and lower limits to the eigenvalues of Lz, because Lz can't be bigger than the magnitude of the angular momentum, that is, L, that magnitude of L. It has to be bounded by that total angular momentum. And so you can't make it bigger than the angular momentum, and you can't make it less than smaller than the angular momentum, more negative than the magnitude of the angular momentum. And so there must be an upper and lower function. And this leads to two limiting relations. That is, L plus applied to the topmost function will have to give you 0. And L minus applied to the bottommost function also gives you 0. Ft and Fb then are the topmost and bottommost eigenfunctions of a particular value of L squared.